Hello everybody, my name is Chen, and this is pre-conference tutorial to SAS Global Forum 2020, Introduction to Bayesian Analysis. So this is the outline of what I will be discussing today. It's a pretty high-level overview of what Bayesian statistics is, and relating to some of the simulation methods that's being commonly used in Bayesian paradigm to do estimation and the modeling. And to the end, I'll introduce two SAS procedures. PROC BGLIMM is on Bayesian generalized linear mixed effects model, and the PROC MCMC is a general sampling algorithm based procedure that has been out for a while, and the BGLIMM is a relatively new procedure. So this is the overview of the Bayesian paradigm, and we started by stating what is statistics and what is Bayesian statistics. So the idea of statistics is the science of learning from data, from collecting, analyzing, and interpreting, and to do inference. And one key is to communicate uncertainty. As we all know, point estimate means something, but usually it is the confidence interval to quantify the uncertainty is what we care about. What is Bayesian statistics? Bayesian statistics is a subset of statistics. A subset of statistics in the larger sense of the word, and the key point that I want to carry is to point out is that all uncertainties in Bayesian statistics are summarized through probability distribution. Oh, that's the key. As confidence interval, on the other hand, is not a probability distribution, and Bayesian statistics, all uncertainties are summarized through probability distributions. So we can, using this 3-item bulletin points to summarize Bayesian paradigm. So in the Bayesian paradigm, probability describes degrees of belief. What that means is what you personally think how likely something is going to happen. So it's a rather personal thing. It's not a limiting frequency. So it's by definition is very subjective. This has caused a lot of controversy throughout the development of statistics, because people find that to be not a desirable thing when it comes to doing science. But from a Bayesian perspective, probability certainly is very much to do with how personally one believes the likelihood of certain event. That's what probability means. And then parameters cannot be determined exactly. They are random variables, and you can make probability statements about them. You can say the probability of theta is greater than 0 is 27%. How likely is 27%? Well, it's lower than 55%. And inferences about theta are based on probability distribution of the parameter. So it's key to have probability distribution describing about the parameter. On the other hand, what we are more familiar with are the frequentist and classical approach, where the underlying assumption is that probabilities are objective properties of the real world. That refers to limiting relative frequencies, that you repeat an experiment, you toss a coin many times, then roughly 50% of the time will come up head, and 50% would come to be the tail. And the parameters, thetas, are fixed. They're just unknown. They are fixed. They can change. So it doesn't make any sense to say what's the probability of something fixed is greater than a certain value. It's either greater than 0 or it's not greater than 0. And because of the definition of the probability based on long-run frequency, all statistical procedures should be designed to have these well-defined long-run frequency properties, such as a confidence interval that if you were to repeat your experiment many times, then 95% of the realized confidence intervals will cover the true parameter. So that's the confidence interval. This is a simple example of how Bayesian thinking in real life works. And suppose that you suspect you might have a fever. That's your parameter, and it's just the unknown, let's say unknown theta that capture what's the body temperature, and they want to take your temperature. And because you don't know what your body temperature is, then you can have a prior guess. You think, well, in a normal situation, if you are mostly healthy, then it's centered around 98.6 degrees, and possibly if you are sick, and it has a range, say between 110 and 104 degrees, and it is used captured by this dashed distribution. Okay. And now you take a measurement from a thermometer, and the thermometer says 101 degrees. So this is your likelihood. This is what we call it, is that the data is generated by something unknown of theta, and hopefully that the thermometer is fairly accurate, then you know that it's probably normal, centered at the true value, and with a small standard deviation or variance. And you put the 2 and 2 together, and then you get your posterior, and then you are sick. So you do that, and this is what Bayesian thinking in real life does. However, on the other hand, suppose that you took a measurement, and the measurement is rather unreasonable. It's either very low or exceedingly high. And if it's very low, and let's say just to be the temperature of 93 degrees, and it is so in conflict with what your prior belief of your reasonable body temperature around is, then you will reject the data. And then the posterior will remain the same as the prior. And by rejecting the data, why we reject the data? Because there is so low prior belief that you could have a body temperature of, say, 90 degrees or 85 degrees. So that reflects on the probability, and and that's how you reject the data, and your posterior then be the same. And so this is the Bayesian paradigm on sort of a more statistical term. And suppose that we more formally want to conduct a study, and then the parameter theta is of inferential interest. And it can be many examples. It can be regression coefficient, it can be missing data, it can be hazard ratio, it can be just the probability of something true, just anything that you want to find out. Okay? And now, let the data let X denote the data, and then this model, what we call density of P of X theta, is the data generating mechanism. We also call it as sampling distribution, is how the X comes about given theta. And we also say that the function itself, that's proportional to this sampling distribution, is the likelihood function. We all know that. That's actually very standard statistics in that. So the Bayesian mindset is that we want to start with this distribution or likelihood that describing data generating mechanism that's controlled by some unknown parameter, and we want to say something about the parameter itself. So it's the switch. It's a switch. Given X, that given theta, we want to say something theta given what we have observed. And the switch from data given parameter, the likelihood function or the sampling distribution, to the parameter given data, which we call posterior distribution, is the essence of Bayesian paradigm. And now the immediate question comes about is, what is the likelihood and what is the posterior? And are we simply switching the likelihood function and just call it the posterior distribution? So this is a picture of, you can look at the picture two ways and you see completely different picture. A young lady and older lady. But essentially the same thing, are we? And it's almost just like that. So it's almost just like that. And the switch, the key to switch comes with using the Bayes theorem. That's attributed to Roman's Bayes back 250 years ago, so in the 18th century. So states that the posterior distribution, in order to make this switch, the posterior distribution of theta given x is proportional to f of x given theta, which is the likelihood of p of x, x given theta, times a prior distribution. Okay. And in fact, it disappears if it is constant. So if pi of theta is 1, then the posterior is indeed the same as the likelihood, functional form. Okay. So the caveat is, what you are in fact doing is you are switching the random variables. From the likelihood is more about the data given theta. It doesn't say anything about the theta. It just says how like the behavior of the outcome of the data is governed by the sampling distribution. Now when you make the switch, the random variable is theta, and nothing to do with the data. The data is given, and then this distribution now describing the behavior of the parameter theta given x. And that's why this posterior distribution is a distribution on the theta and not a likelihood, which is a distribution on the x. Even though functionally they are the same form. And in order to do this, you have to go through the joint, the marginal, and the integration with respect to theta at the, this is called a normal random constant or marginal distribution of x. And this is the formal Bayes theorem is the following, but mostly people using the one on top for it. And this is also the requirement to do Bayesian statistics is that you must always use a prior distribution. You cannot have an analysis that bypass the need of using a prior distribution. And unfortunately, it also cannot be constant all the time because the posterior is not guaranteed to be proper with respect to a flat or a constant prior. The reason is because the likelihood distribution or sampling distribution required to be distribution with respect to x. So it's proper with respect to x, but it doesn't say anything about theta. That's not the job of the sampling distribution of the likelihood function. But in order to make this thing proper as a distribution, there must be something done. And so that's why you cannot always use a constant all the time for the posterior. Once you have the Bayesian analysis framework on inferences based on distributions, then you can say, oh, how about this Sumerian concept of different point estimation and interval estimation? And an estimator essentially just an estimate of the best guess from a distribution. And the Bayesians typically use posterior mean, the expected value of theta with respect to a distribution. Okay. And you can use them all, but mostly people use the expected value of theta given x. And then the interval estimates, the Bayesian concept is called credible sets. And it is the area under the curve, essentially, 95%. And you can have many, many different areas of the curve, but most commonly people use equal tail, two side, alpha minus 2, alpha, since distribution doesn't have to be symmetric. And at highest posterior density is the smallest interval that contains 95% of the probability mass. As the interpretation is, there is a 95% chance that the parameter is in this interval. The parameter is random and it's not fixed, so you can say that. In the classical approach, the estimator is a confidence interval. It certainly has very nice properties such as convergence probability, coverage probability, not convergence probability, coverage probability, minimum false coverage, unbiasedness, and so on. And as the interpretation is that a 95% confidence interval asserts that if you were to repeat the experiment many times, 95% or roughly the realized confidence interval covers the true parameter. You cannot say the true parameter is in the confidence interval with probability 95%. The true parameter is either in or outside of a confidence interval, but not with any measurable probability. So the interpretation reflects the uncertainty in the sampling procedure, because the parameter itself is fixed and the interval is random. Okay. And now we're just going to discuss a bit about two major criticisms on Bayesian paradigm as a way to understand the approach better. So the first criticism is, should a parameter be fixed or random? And the Bayesian's perspective is that whether a parameter is fixed or random is somewhat beside the point. Either it's fixed or it's random, we still need to quantify the uncertainty about it. And the best way we know how to do it is to use a distribution to describe the uncertainty. And that has many benefits to it. The answer is that we don't really know, but the important thing is to quantify uncertainty. And then the second criticism on the Bayesian paradigm is that a prior distribution contains too much subjective information, as in the sense that we are being too subjective and our own belief is driving the analysis. You'd be surprised how often this happens. And the fact of the matter is that scientific inquiries are subjective by nature. We in fact don't look all at the same data and reach identical conclusion. And if we do, then there is no point. We all have to agree, but in fact that we don't agree. And Bayesian just being honest about the whole process and simply reflects how general scientific inquiry works, which really rely on each individual bring their own opinions and knowledge in the process. And you believe something works, or you are skeptical something doesn't work, and we all get together to see and based on data to improve or correct our opinion. And so there is this famous saying by John Keynes, is that when the facts change, I change my mind. And so that's reflecting updating the prior to the posterior just being set. And on the other side of the equation, yes, much of the statistical modeling, we got to remember that, is subjective. The selection of the likelihood function, the arbitrary cutoff p-value of 0.05. So the completely elimination of subjectivity and retain objectivity is really not, it's desirable, but it is not really practical in any sense of the word. So here are the two sources. And we can also have another look at p-value. So that this contrasts between Bayesian and frequentist. And so let's say this is a survey done by about probably 40 years ago at this point. So the survey says, what would you conclude if a properly conducted randomized clinical trial of a treatment was reported to have resulted in a beneficial response of p is less than 0.5 significance? Okay, so what are these things? All right. Okay. So here are the four choices. One is having obtained the observed response. So having seen the data, the chances are less than 5%. The therapy is not effective. So the probability of therapy is not effective is less than 5%. That's a statement about on the therapy, and it's likely to be wrong. And now there's two confusing and equally confusing statements. Is the chances less than 5% of not having obtained the observed response if the therapy is effective. So you set the therapy to be effective, you assume to be effective, and you say that there is less than 5% chance of not observing. Or you set the therapy, the now to be not effective, and to say the probability is less than 5% of seeing the data that you have. Okay, or the fourth one is not really. And the survey asked 24 physicians, and half answered incorrectly, and all had difficulty distinguishing the subtle differences. What does it mean? That you assume therapy is effective. What it means that therapy is not effective. But of course, to a trained statistician, this is bread and butter. You set the null to be not effective, and then you look at the chances of something happens. And then the correct answer to our question is then 3. Okay? Now, this isn't right, and this is even wrong. And this is written by Wolf Pauli on a submitted paper. And the correct answer is that the chances are less than 5% of having obtained the observed response or any more extreme response if the therapy is not effective. Okay, this is really a mouthful to interpret what does less than 5% means. But that is the definition. You got to integrate out the observed likelihood of seeing the observed response and a more extreme response. That's what p-value is. And this is the interpretability that Bayesian and the frequentists often differ on. That is that you can reject the null, you can never accept the alternative, and so on. But and as a result, it is often being misused in practice, and people really think p-value and the confidence intervals indicate the probability about the hypothesis, and they use them as evidence for or against the question of interest. But that's not. That's really what Bayesian approach does, and that is what's advantage of having sort of Bayesian inference in that sense. And in addition to the interpretability, Bayesian also offers certain modeling advantages, which I won't go through here. But because of treating unknown quantity as parameters can be estimated, it leads to a very easy solution to the setting of complex problems so far, and bypasses need to derive asymptotics for that. And there is also a formula of learning, which I will skip here, because it just says that as you updating your data, you will becoming more and more certain or not certain about a parameter, and distribution will be updated and so on. There are some additional Bayesian advantages, which I'll leave the attendees to look them, because I think you all have the handouts, and I won't go through them at this point. And I will move on to the next session. So next we will talk about prior distributions, which is an important aspect of Bayesian analysis. Prior distribution, as we had mentioned earlier, represents your belief before seeing the data. It's what you believe in. And the Bayesian probability measures of degrees of belief that certainly you have in a random event. So by this definition, probability is subjective. There's no way to go around it. It follows that all priors are subjective priors, and the people don't like the word of subjective, even though we had discussed of the subjectivity in all the sort of scientific inquiries and inference. But people still want to see and obtain the data results that are objectively valid. And so the saying is that the data speak for itself, and don't tamper with the analysis and so forth. And this approach advocates non-informative prior. They're sometimes called flat, improper, and Jeffreys priors. And then the other side of the coin, the subjective approach advocates informative prior, just to say that combined what the knowledge that you have in the analysis is just how we advance our understanding on things. So generally speaking, the amount of data grows in a model with fixed number of parameters, so the likelihood typically overwhelms the impact of the prior. Generally, that is held to be true. And I want to discuss a few prior that's for in this section. A non-informative prior. A prior is non-informative. It has a very vague definition, and we'll see why the definition is vague. A prior is non-informative if it's a flat relative to the likelihood function. And the desire is to have minimal impact on the posterior of theta. The reason a lot of people like non-informative prior because they appear to be more objective. But it has been proven now at this point, 25 years ago, that Larry Wasserman and Rob Katz written a paper to say it's unrealistic to think that you could have a truly non-informative prior that represent total ignorance about a parameter of interest. And a common example is the following. If you are to model a regression model, height as a covariates and a predictor to the response as a weight, you more or less know what the regression coefficient need to be. It cannot possibly be anywhere from negative 10 billion to positive 10 billion. You'd probably be shocked if the height and weight, ratio and it's greater than say 100. It depends on the unit, of course. And now, if you have a flat prior, you think that you are non-informative and you want it to be completely non-informative about things. You have a uniform prior from negative 10 billion to positive 10 billion to say this is anywhere my coefficient could be, and I don't know what values I take, so I have equal preference ahead of my analysis to say that they can be anything. But from a distributional perspective, you know that you're putting massive amount of prior mass, greater than 99.99% outside of possible range. That just means that a priori, you already don't believe the results that you will see. That you are much more likely to believe that the coefficient of a regression coefficient is greater than 100 and less than negative 100 from the range of negative 10 billion to 1 billion, or negative 10 billion to positive 10 billion or something. So that's the concept of you can have no non-informative prior representing total ignorance about the parameter of interest, and that's a key point. And but that's not stopping people from using it or calling this to be non-informative. And then the frequency non-informative prior is proportional to 1, which assign equal likelihood to all possible value of the parameter. And that's just the way it is. And if people do call it non-informative, even though that it contains information. That's a key point I'm trying to get across. And here I'm going to use an example. It's a binomial example. And suppose that you see 14 heads in 17 tosses. And your likelihood is binomial with x is 14 and n equals 17, and the p is unknown. Now we're going to do a flat prior because I don't know what the theta is going to be before. It could be 50-50. It can be it can be worse than this. It can be higher than that. I don't really know. So I'm having a flat prior of p is proportional to 1. And now I multiply the two together. I get a posterior distribution, and now you can see 1 times this gets to be here. But now notice that the random variable is x. So p is fixed, x is unknown. You plug in x and n to be a likelihood, and now the x is known, and the n is known, and the p is unknown. So the random variable is p. So this is a binomial, and this is a beta distribution, kernel of a beta distribution. And this is the part that we can see is that you have a binomial model with a flat prior. The posterior is identical to the likelihood function. The flat prior is used, and then just a few observations I'd like to state. And first is we had already observed if the posterior is equal to the likelihood with prior is flat, then why not use the flat prior all the time? The reason is that the flat prior doesn't always guarantee the proper posterior distribution. This quantity needs to be a distribution. And you ask, why is that we start with the likelihood function with a proper density, and you slap something flat, you end up with something improper? That's because the density function is proper with respect to x. But if you translate to likelihood, it often has a mode, but the likelihood function doesn't care about the tail. The tail doesn't need to go down. So the likelihood function is not guaranteed to be integrable. And that's why if you have flat prior, it's not always guaranteed to be integrable. You don't have tail that weights the things down. And so when in doubt, you should always use a proper prior to weight the tail of the likelihood down to make the thing a proper distribution. And then the second observation is, in case where the likelihood function and the proper posterior distribution are identical, do we get the same answer? This is the zoom-in picture of this binomial around the mode here. Okay. And you can see there are two curves. One is the black curve, this is the posterior distribution, which is also identical to the likelihood. And then this is the MLE, and this is a normal approximation around the MLE. Okay, that's the classical inference that is based on asymptotics, the central limit theorem, normal approximation. And the Bayesian inference is based on exploring the entire distribution, which that's why it has skewed to the left to come to the right. So key takeaway is that you always have to defend something. By that, I meant is that everyone, in a sense, are slave to the likelihood function. This is the foundation of all both paradigm. The x given theta is the data, is how we use to do inference. But given that, in Bayesian paradigm, you often need to justify the selection of your prior. But in the classical paradigm, you need to adjust asymptotics. You need to know why this curve is becoming normal. Okay, and that's quite a bit of amount of work. The underlying assumption behind asymptotics is there exists an infinite amount of unobserved data that are just like the one you have seen. Okay? Whether that's true or not is up for debate, and it needs to be justified if you want to use the classical paradigm. If it's true, then of course asymptotics all follow through. But the Bayesian makes no such claim. Bayesian does not make a claim that you will see more data than what you have already seen. If I see 14 tosses, 14 heads out of 17 tosses, that's all the data I see, and I don't assume what's going to happen with the 18th toss or 19th toss, or similar tosses, in that sense. And then the third observation is, when it comes to flat prior, is flat prior truly non-informative? Okay, so let's suppose that in the binomial example, what we did is a flat prior on P, and we get the likelihood and the posterior. And suppose that instead of modeling on P, I choose to model on larger P. Okay. So a uniform prior on P, which is the left-hand side, as you can see, it's a flat line between 0 and 1 to 1. If you transform a variable to gamma of larger P, the prior is a logistic distribution. This by no means is going to be flat. Okay? You can't say this is very flat. I skipped the way to do transform of variable. It's a Jacobian thing. And on the other hand, if I were to choose a non-informative, just being assigned equal likelihood to all parameter values on the larger scale, I translate back to this Houdin prior is peaky on both sides. So because there's so much weights outside of logic, I mean anything outside of a reasonable logic, like 5, -5, is significant. And now if I say I'm going to be impartial to all logics, hundreds, -1,000, 110,000, then just means that I much more prefer to do the analysis by thinking it is either 0 or 1. Okay, so this is a way that, and why is it? Why is that so hard to have a non-informativeness? Is that a flat prior often implies a unit, sort of a measurable scale on which you assign equal likelihood. And then when you say it's 1, you are saying that theta is likely to be between 0 and 1, and the 1 and the 1,000 and the 1,000, 1,000 and the 1,001. But if you want it to be uniform on the log scale, then it's likely to be between 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, that type of unit. One obvious difficulty is in justifying when you pick a specific flat prior to explain the choice of the unit which the prior is being non-informative on. And that's a tricky thing to do. And that you always have to bear in mind when you do that. And so people will say, do we have a prior that's somewhat non-informative at the same time is invariant to transformation? And then the answer is Jeffrey's prior. And this Jeffrey's prior, I'm just going through this very quickly. It's just it depends on the expected Fisher information based on the likelihood function. Okay, so the likelihood is telling you how to construct a prior, and you can see the example of how it goes through the math. It's not very difficult. It takes the derivatives and plug in the value, and then you can compute it. And then the plot I'm seeing here is this plot, and this is Jeffrey's prior. It tails upwards because the opposite of the likelihood. Likelihood goes down, it tails up, but it is flat relative to the likelihood. And so the likelihood is solid. The posterior shifts a bit to the left. Okay. And then the nice thing about Jeffrey is the Jeffrey invariance. It's just you are non-informative on one scale, you are non-informative on all scales. There are some pros and cons about Jeffrey's prior, which I will skip here because it's only a 2-hour tutorial, and this is really for something that you would want to take a look maybe later on once you have the slides, and how it violates the likelihood principle and so on. There's some pros and cons of the methods which I will go through. But what I want to finish with this session is a logistic regression example with zero occurrence, to see that how Jeffrey's prior utilizes likelihood information. It can be quite useful. So there are 4 treatment groups. Treatment is 1, 2, 3, 4, and the response is Y. The number of patients given the 4 different treatments improved out of the total number of N. So the ratio. Okay. So group 4 having no incidence of event, it's all zeros. And now if you're going to do this model, standard likelihood-based methods are now usable because of zero occurrences, and you got to have other ways to associate compute standard error. And now we can compare using the uniform prior and the Jeffrey's prior analysis in here. And this is just a data that I see. That you can see 4 group 1, 2, 3, 4, and 1, 2, 3, 4, and then there is the number of response in each of the n number of trials. It's a binomial model with treatment, logistic, and the Jeffrey's prior is this piece. Okay, X transpose M transpose X, and M is a off-diagonal elements of P and P1 minus Pi. And now this is the blue line is the Jeffrey's posterior, which you can see that when and the red line is using the uniform, and it can't estimate the last group. Okay, just no information is in there whatsoever. And you can see that the 2 things to point out. The Jeffrey's line borrows information from some other group to infer, to at least give you some signal on what you're likely to believe, given the underlying model assumption. On the other hand, it doesn't change much of the posterior distribution of other parameters that have uniform prior. So Jeffrey's prior, in the sense, is designed to do what it does, is to be non-informative in many situations and helping by borrowing information from the likelihood to do some inference of other groups. That's what I mean. And the last is the conjugate prior. And we're done with the non-informed prior, just moving into the conjugate prior. And the conjugate prior means that a prior and a posterior are of the same form. So if you have a likelihood distribution of the binomial, a conjugate is a beta prior, because the posterior is also a beta distribution. And people like to use conjugate, not for computational reason, for that reason, but also because that you can look at the prior and understand the amount of information associated in the prior. So the data contains X success and out of N trials, and the beta prior with alpha and the beta scale and the shape parameter indicates alpha success out of alpha plus beta trial. So you look at beta 22 and the beta 317, you know clearly what information that they represent. And then on the same idea of looking at the data by containing the information is this thing called unit information prior, that's designed to have a prior that contains roughly the same amount of information as the one data point. So this is also, as you can see, is using Jeffrey's Fisher information based on one observation prior kind of to do this. And the last thing I want to say is that informative prior, in a way, when it's used properly, you can use existing information to carry through in your analysis. And when it's used properly, it can be very powerful. But of course, you can also get very misleading results with it. The last thing about prior that I just want people to be aware of, I will also treat this as a skip for people to read through, is called a prior elicitation. So the idea of prior elicitation is that you know there is expert opinions on something that is increasingly important, but they don't know how to translate their knowledge to the model of the distribution on the parameter that you have. So they might have some knowledge in the field, how something works with something. Compound A impact the outcome of B, but because they can't translate that information to the prior distribution of parameters in the model. So this idea is called prior elicitation. That experts only be asked to assess observable quantity, but you want to translate information to the parameter, and I work through a idea of prior predictive distribution, and then how to elicitate a coefficients if you want to conduct study on height to weight what prior you can use on beta. And I will skip this part due to lack of time at this point. So for basic computation, there are two tasks at hand. The important thing is to estimate the posterior distribution P of theta given y, which needs to be accurate because this is the basis of all Bayesian inference. And then the second task is to finding expected values, point estimates, which can come in two forms. Both are based on this distribution. One is the expected value of theta, just the parameter itself, okay, or expected value of the function of theta with respect to the posterior distribution. So I could say that I want to know the expected difference between two parameters, beta 1 minus beta 2. So they can be functions of theta. So these are the two things. And for decades, the most popular method for estimating the posterior distribution, task 1, is through MCMC, Markov Chen Monte Carlo. And I'll explain why that is to be of exceeding importance. And once you get this MCMC, once you get the Markov Chen Monte Carlo to estimate this distribution, the second task becomes rather trivial. You can just plug in for values and this type, and it's very much doable. So essentially, Markov Chen Monte Carlo solves two things. And then the Monte Carlo aspect of the second part is to find an expectation of g of theta with respect to a sample from a distribution P of theta. Is you just generate many samples from this distribution, evaluate them, and take the average, and you find the expected value. So that's why it's kind of a trivial. This is a plug-in methods, and then you can do it for big dimension that you want. It's accurate. Going back to the simulation-based estimation, so the idea is you sample by proportion. This is the distribution of a beta distribution. The true density is the black line, and the red line is the estimate density, and the histograms are the samples of the realized samples, and you can, if you sample right, you can estimate the distribution to any degree of accuracy. Of course, there's two major obstacles. One is there is this normalizing constant. So for a distribution, you know, it's proportional to some kernel over a numerical constant. For a normal distribution, we know what the normalizing constant need to be. But for arbitrary distribution, it's unclear. And then the second is the theta dimension is high. It's actually very, very high. So this difficulty was the first difficulty of this problem. Sampling without a no, you have a target distribution, but you don't know how to sample from. This problem was solved by Umar and Metropolis, who essentially says that to sample from any target distribution, you need to just construct a Markov chain that has the stationary distribution to be the desirable distribution. So instead of generating directly from a target distribution, so an example of it is the normal random number generator function, R norm in the norm function, the rand function in R, in SAS and R norm in R, you can simulate from a Markov chain instead. Okay, once you do that, you ended up with sample from the target distribution. Of course, how to generate Markov chain is secondary, but the problem they solve is they just stated that if you can construct a Markov chain with a standard desired distribution, the target distribution to be the posterior, that Markov chain is guaranteed to be the sampling of that distribution. Okay? And the how part is the Metropolis-Hasting algorithm. And then the Gibbs algorithm changes the landscape of the simulation-based computation. Essentially, that's why everything is going through the MCMC. Okay. Going back more formally to define Markov chain Monte Carlo, it's just a stochastic sequential way of generating conditionally independent sample according to some distribution. That means that you started from a sample theta 0. Given theta 0, you sample theta 1. The theta 1 can depend on theta 0. Theta 2 can depend on theta 1 and theta 0, and so on and so forth. But the Markovian property is that the sequence of conditional data that you have had only depends on the most recent ones. So given the most recent ones, you sample the new one. Given the new one, you sample another one, is forming the basis of a Markovian chain. And here is a list of a lot of papers and articles and the books that devoted to MCMC, and you can check them out. Now you say, where does the thing idea Gibbs comes in the picture? The Gibbs come in the picture because MCMC in high dimension problem to be too difficult. So Gamma paper in 1984 showed that you can break a larger problem into smaller problem, much smaller dimension, and you can still get what you want, the collection of the sample from the joint distribution. And then they also show the conditional distribution can jointly determine a unique distribution. So everything worked out. It's actually very good. And that's just to show a picture of how the step, and I think many people are familiar with this concept of Gibbs sampling. So suppose I want to draw a sample from alpha and beta distribution. And I start with alpha at alpha 0. So this is the value of alpha 0. Just pick a random number for it. It's called initial value. And condition on this piece, and you can see that there is a slice over the joint distribution. This is called conditional distribution. This is the beta. This is drawing a sample on the beta dimension. And of course, this is probably higher here and the lower there to the tail. And you have the distribution, and then you sample and you get a beta 0. Okay, just draw a sample, and you turn around and you look at the other way, and this gives you the marginal distribution of alpha given beta. And you sample along this marginal distribution, conditional distribution. You do it one by one, and you repeat this many times, and this is what Gibbs sampling does. Okay. I was going to do this simple example of a normal hierarchical model, Gibbs sampling, but I will skip this because due to the lack of time that we have. This is the material. It's not too difficult to follow through. You can get an idea of how to do Gibbs in this particular situation. The key quantity that I want to point out is that each of the conditional distribution is of a standard distribution. And the standard distribution is you can utilizing a standard distribution for each of the step, and that has been done many years in Bayesian computation. This is where conjugacy sampling became so important. But of course, not all problem can have conjugacy, and you can certainly have problems that conjugacy doesn't apply, and then you get a distribution that you don't quite know sample from because it's not a standard distribution. And this is need a general sampling algorithm. And this is where the Metropolis algorithm comes in. So the Metropolis algorithm essentially it's a general sampling algorithm that puts minimum amount of requirement on what one need to know the distribution that you are sampling from. So it's sort of like a magical thing. All you need to know is the density of the distribution, the functional density of the distribution as some random number generator. And then you'll be able to do this. And then here's a picture of it. And let's say that I want to draw a distribution from pi of theta given x. Okay. I don't know what the shape of it is. It's certainly not any distribution that I know of, but I still need to sample in a proportion. So what I do is I started with some guess of initial value of theta. And then I say I'm just going to randomly draw centered where I am from a normal distribution of theta mean at theta 0, giving theta standard deviation of sigma. And then I get a theta star. And then now what I do, I'm going to make a decision if I want to accept the sample or reject it. And the decision rule is such that if where I'm going to, the theta star, has a higher posterior density variation, a preferred place, I always move there. Okay, so I'm moving from theta 1 to become theta 0 to become theta 1. So that's the second sample of the Markov chain. But if I propose to somewhere where it's lower, and I compute the height of the density of this height and this height, and I know this is lower, then I accept the sample with a probability ratio between the height of this to the height of that. Okay, so that's Metropolis. And then I keep going. I repeat the same process. And the idea is a Markov chain always move to the area that have higher density, but it can still explore tail area with low density. And if I do this repeatedly, I'm guaranteed to sample by proportion of this arbitrary distribution. And this is a random walk Metropolis algorithm. So this is the trace plot of a random walk Metropolis. To sample from a normal distribution, you see that it started, let's say that I started from a very far from normal 0, like around 0. I started from -20. The Markov chain gradually moved quickly to the center of the distribution, and then it stays there. You can see it mostly stay around mean 0. But it goes to the tail end, and the result is this distribution that's normal density. If you do this long enough, it can approximate normal 0, 1 to arbitrary degree of accuracy. So there's pros and cons of it. There's pros and cons of Metropolis algorithm. It requires minimum requirement of the knowledge about distribution. So it's very general. It's easy to implement. It's robust. And it can relatively be slow, and it certainly requires convergence diagnostics and whatnot. But the key point that I want to come across is the Gibbs sampling algorithm breaks a larger problem into a small problem. The UMA and the Metropolis idea of using Markov chain to sample any arbitrary distribution has simplified a difficult problem. And the Gibbs steps tells you that you can break the bigger, larger problem, a bigger Markov chain into very small pieces. And the Metropolis algorithm takes away the requirement that you need to know about certain parameters distributions in their Gibbs conditional distributions. And that's important in the sense now many problems becomes doable. And there has been the development for past 25 years and still ongoing. It's still, you can see a variety of general sampling algorithm to that sense. And the newest kid on the block is Hamiltonian Monte Carlo that came out maybe 10 years ago. But recently, more and more people are getting into it. It's an alternative way of generating samples for it. And I'll quickly go through this. Again, it's fair to highlight concept and show some plots and pictures and for you to get a sense of this, how this thing works. Okay. So Hamiltonian Monte Carlo is, uses two things that's, expensive, by comparison, much more expensive than Metropolis. One is it asks for first order gradient information, because gradient typically helps. Metropolis does not require gradients information at all. And second, yet it creates this thing called auxiliary momentum variable. And it's like a latent variable kind of a thing to help you to sample from a high dimensional joint distribution. The idea of Hamiltonian, because of the physics, the Hamiltonian dynamics, and because of utilizing Hamiltonian dynamics, you can generate samples that are very far away from the current sample and making efficient in many cases. Okay, so the gist of the idea is you have parameter theta, and this theta can be high dimensional, say 50,000 dimension. And then HMC introduced a momentum variable R, which is of the same dimension. So it's 50,000 more dimension. You essentially double your parameter sampling parameter space and hope that you will do better. Okay? And often it does. And now on the very form, it results in this density, which is going to assume this has a form of exponential of U of theta and the K of R. And the U of theta is to be the negative log posterior distribution, which is okay. And the K of R is going to have this kind of this form, quadratic form, half of R transpose R. And you can see that this came as a normal kernel. That's why this thing is designed to be this way. There are various different terms for it, but essentially the two things you should think that one is a positional and one is momentum. So you think of theta of U is called potential energy, and K of R represent kinetic energy, and the 2 of 2 remain to be constant, because on physics, that as long as you remain constant, you reach an equilibrium. So the key is how to put them in making them constant. And let's forget about this HMC leapfrog. This is how one actually moves in the Markov chain, but let's just see a picture of it. So you have theta, and you have a density. This is just arbitrary picture representation of the, say, posterior distribution. Okay, and I have theta 0, and I have this U of theta, and again, this is this piece. Just think of this as piece U of theta. This is the potential energy. Okay, and let's say that this is potential energy, and now I have a sample of R of 0. Okay, this is the kinetic energy. And how to do it? How to do it? Let's suppose that if we know how to do it, and that's what the leapfrog thing was for, that we skipped in the previous two slides. There's a formula how to do it. Now 2 and 2 to add together, you create a Hamiltonian equilibrium. Okay, and now the key is you gotta find a clever way of moving along this Hamiltonian equilibrium which translates, it's not quite like this Hamiltonian, but on high dimension, it's like a contour where around the edge is all very the equilibrium. So you can move anywhere along. How to move along is a leapfrog, and you leapfrog around it to get to a new point. And once you get to the new point, you create additional potential energy, which is the density variation, and the kinetic energy, and you form a new contour that lets you sample. And then the Markov chain moves more rapidly because of this. And here is a picture of it. To the left is a Hamiltonian Monte Carlo. To the right is a Metropolis. And it's generated from a regression model. You can see that to the left, the chain moves much more rapidly than to the right, even though they all commit to the same thing eventually, but the mixing is better and Hamiltonian than Metropolis. There's some details in the leapfrog, how many steps that you have to do, how big, how wide of step in the leapfrog you have to do, and how many steps you have to do. Now comes the no U-turn sampler. It's sort of automated way of generating HMC samples, which I will go through in here. And this is one of the more becoming more popular methods in sampling from a joint posterior distribution. The next part we'll discuss about some benefits of sampling-based methods. Sampling-based methods, by and large, is not the fastest algorithms in the world. By comparison, they are much, much slower than maximization and optimization. Because optimization is essentially line search. You want to go to the top, find your MLE, and quantifying of uncertainty came from asymptotics and the formulas and easy to calculate. But Bayesian is responsible for sampling the entire parameter space, and that takes time and it's slow. So, but there are undeniable a lot of benefit in sampling-based methods, and here I am going to provide some retrospect on the matter. So the simulation-based algorithm can provide, like I said, but they just tend to be slow. A more important question is, when you do inference, what you want is a marginal distribution. So if the interest is on the variance, you want the posterior distribution of the variance distribution, P of theta y, sigma square y, given y. While the Gibbs sampling algorithm generates samples from the joint distribution of everything. So here just, this is the notation coming from an early example of normal hierarchical model sampling with all these parameters. By essence, what you want is P of sigma square y given y integrate out all other parameters which can be exceedingly high dimension. This is not, numerically, this is a hard thing to do. Okay? But as it turns out, as far as MCMC is concerned, this is trivial. So here is the idea of joint distribution. That you sample alpha and beta, so pairwise they came from a joint distribution. Alpha and beta, this is alpha dimension, this beta dimension. Okay, so you run your Markov chain, you sample your Gibbs, you sample alpha, and you get beta, and you can sample alpha, and you get beta, and so on and so forth. And now the marginal distribution of alpha of x is in essence the collection of all the alpha samples, and you can throw away the betas. Okay? So this is almost magical. in the sense that you throw away in any Markov chain, you throw away things you don't want and you keep what you have, you get your marginal distribution. So this numerical evaluation is trivial if you have a Markov chain, Monte Carlo chain, a Gibbs of the entire parameter space, and you, in essence, you throw away all these samples to keep what you have, you get yourself a marginal distribution. There's a reference paper, there's a paper on explaining the Gibbs sampler, Cassandra George in 1992 that explained this phenomenon. And so this is what saves the day, because for any Markov chain Monte Carlo, if one has to do some intense numerical marginalization, nobody would ever deal with MCMC. But MCMC is you get the sample from the joint distribution, you get the rest of the things for free. In addition, that you can compute any functions of parameters directly, such as a difference in treatment. Okay, what that means is the following. So imagine in the classical statistics approach, you do plug-in methods. If you want to estimate alpha minus beta, okay, so you plug in MLE, it's called plug-in method. And how do you do with standard error? Is you have to use delta method, central limit theorem. You gotta make sure that the tail goes down correctly and things work well. The big O n square over 2, n cube or n square or whatnot. That the tail go down sufficiently fast is a function of the sample size. But with MCMC, you don't have to deal with any of this. You don't have to deal with, if this function itself is exceedingly difficult, it is unclear whether you'll be able to figure out the clever way of to do delta methods and whatnot. And with MCMC sample, you just plug in. You plug in one by one and you get a posterior distribution of the entire thing. So for example, if I have alpha and a beta, and I can compute the distribution of alpha minus beta just by pairwise computes the function of each one. And you can do as complex of differences as you want. And you just plug in, you have your function, and you plug in every value, and you get a distribution. Okay. And then what the Monte Carlo average also lets you compute the expected value as well. You can say the probability difference greater than 0 given data is the number of samples that fall to the right-hand side of 0. Is say 49%. So MCMC is you pay the difficult price ahead of time, and once it's done, all subsequential analysis is almost trivial for that reason. That's why MCMC sampling algorithm has been so popular because the stuff that you can do with it bypass a lot of needs to do difficult computation statistics. Right. The last thing I want to talk about is Markov chain convergence, which is an important aspect of it. Convergence just means that the Markov chain need to get to the target distribution and stay there and sample by proportion. And of course, the faster the better. It's called good mixing. And random walker algorithm can explore the parameter space, but it can probably take a long time to do it. However, that's a question of efficiency. Okay, that's not fatal in the sense that as long as the Markov chain is sampling the posterior distribution to the appropriate density, slowness does not lead to biased estimate. So the goal is then to determine if you have gathered enough samples to accurately estimate distribution. Unfortunately, there's really no definitive test of convergence. But that's more or less is same true with all numerical methods. And like we never know we've reached a global maximum, for example. I mean, it stabilizes computationally. Same idea is running Markov chain diagnostics, that you need to have some numerical support or visual support that the Markov chain has stabilizes and is sampling from a stationary distribution. And trace plot still reigns supreme for this reason. You want to have a distribution, the marginal density is smooth, and you want a trace plot that stabilizes, has whisks that go to the tail, means explores the tail area, and it comes back to the high density area. Okay, so the confidence sign. And you can, various trace plots, you can have a good trace plot on top. And the second line probably indicates you need some burnings. Burning just means that the initial value of the Markov chain Markov chain value need to be discarded, and then the remaining stays. But if you do see a trace plot like this, it's indicating non-convergence, and you probably need to deal with it, modeling a different sampling algorithm, and so on and so forth. That's a more serious problem. What I kind of want to go through the cases here. If you have a train, if you have a Markov chain that looks between the good and the bad, something like this. It stabilizes, but it's moving slowly. What to do? And do people actually, a lot of people think that they want to do thinning. So the idea of thinning is to reduce autocorrelation. So on top, I have a chain of 50,000 and has high autocorrelation to do that. And then now if I thin it by 10, this means I keep one of every 10 samples. I go the first sample and the 11th sample, 21st sample. I discard the remaining, the rest. I can reduce autocorrelation. Autocorrelation just indicates where I am here, can more or less tell where I'll be next. But if it's autocorrelation 0, means it's jumping randomly around. I can't somehow predict. So this just means the chain moves slowly. And you can do this. You can throw this in here. Okay. But on the other hand, you got to know that you are reducing the sample from 50,000 to 5,000. And while this have a decreasing of autocorrelation, means that between sample and sample, there's less correlation and almost pseudo-independence, you are throw away 90% of the samples. So the thing is whether you should do that's something you should do or not. So there are two things to keep in mind. One is you want to ask, are there any danger of keeping the remaining 9 copies? Do they do any damage to you? Do they bring any unbiasedness or change the value of the expected value in your Markov chain estimate? The answer is no. Okay. Autocorrelation does not lead to biased Monte Carlo estimate. That has been proven, and there's a paper that you can read about it. The second point that I want to go through is when you thin by 10, it's a very arbitrary number. You essentially saying that I'm keeping 10% of the sample, any 10% would do. The remaining 90% is giving away not because they are bad, just because they are unlucky. And each one of them will just be as good as this current copy. So you can imagine the 9 other copies, any other copies would just be the same good as this one. So they collectively would, in fact, bring some information to you in estimating it. In addition, when you think about Monte Carlo, the order doesn't really matter. It's not asking how these samples come to you. The order matters in estimating the point estimates. So by and large, you want to think in this way that these are just samples. Including them don't really hurt the estimate, and excluding them reduce efficiency. The general advice is, unless storage becomes a problem, you are better off keeping all the samples for estimation. So that's two things or not two things. I will skip this. Is quantitative measure of mixing. This is a concept of effect sample size. I like using sample size as a way to quantify convergence and whatnot. But this is something that you can read. And next, I will go on to talk about the software, PROC BGLIMM and PROC MCMC. Okay, PROC BGLIMM. Okay. We started with an overview of the procedure. So PROC BGLIMM, you can think of PROC BGLIMM is a Bayesian cousin to the mixed and the grid mixed procedure that specializes in generalized linear and the generalized linear mixed effects models. But it just does Bayesian things for it. Just a quick review. A mixed model contains fixed and random effects. And the normal model, the representation that we are familiar with is y is x beta plus z gamma, and y can be a vector. So that's being mixed and repeats. That means the error terms are multidimensional, and we can do multidimensional normal. And if this is a single dimension, this is just a variance. And the gammas are the random effects, and the betas are the fixed effects. Fixed just means it's the same for all subjects in the population, and the gamma just means you have clusters of informations. And the gammas, the clusters indicates normal 0, variance of G, and it can be covariance if the random effects themselves are vector in form. We call this G as a G side and R as R side, distinguishing the two different covariance on the random side and on the residual side. In PROC mix, we use random statement to specify G side, and the repeated statement is in PROC mix for the residual covariance matrix. The extension of a generalized linear model again is this: you have same linear predictor x beta plus z gamma, and then it links to the link function to the expected value of the y, log-link, prob-link, whatnot, and log-link, and then the likelihood is exponential of m. That makes a generalized linear mixed effects model. In PROC mixed and PROC limits, you integrate out the random effects to get the marginal likelihood, and you're maximizing to get the solution for beta, the G, and the residuals, the R's, and that's how you do estimation and inference. Typically, normal approximation, Gaussian quadrature, and so on and so forth. To Bayesian, you need to assign prior distribution. And the parameters in a generalized linear mixed effects model are 4 classes: the betas, the gamma, the G, and R. The gammas have normal 0 on variance G. Then you have to give prior for beta, prior for G, and prior for R. And once you specify that, then if it's a generalized linear mixed effects model, and you can sample from the joint posterior, that's what the job of PROC BGLIMM does. You just sample from the different joint posterior distribution of such things. Okay, and PROC BGLIMM has simple syntax, very similar to mixed and the PROC mixed. And the essential 3 statements, the larger ones, are the model, the random, and the repeats. And we'll see examples of them. You specify the response variable, and the covariance, fixed effects, response distribution, link function. That's the job of the model statement. And the random, you add on the random effects of Z, and then you want to know what type of G-sided covariance matrix, maybe that prior R. And then if you have repeats, you specify the R-side covariance structure for the repeat statement. You have a class statement is a categorical variable. You handle categorical variable, and then you have estimate statement to compute a linear combination of parameters after the fact. Okay. There's some additional features of BGLIMM. Yes, there's a lot of covariance suites. There may be 13 of them for both G side and R side. And you can, because you have R side, and you can do repeated measurements, and it supports balanced and unbalanced samples. The covariance heterogeneity is a way to model. You can have different subgroups that have different covariance structures that's the same within the group but different between groups. So covariance heterogeneity. It assigns default non-informative prior, and if you think that the analysis requires additional input or different prior, there's a suite of priors that you can choose from. It also computes DIC. It can handle missing data, missing complete at random or missing at random. the algorithms themselves, sampling algorithms, are parallelized to utilize multi-core to speed up computation. Here are some examples. It simplifies this model specification, and we started by a simple linear regression with all interaction between two class variables A and B. This is just familiar syntax. This is standard SAS syntax for any regression model with A bar B of L interaction between categorical variable A and categorical variable B. And a PROC BGLIMM, you have input data set and you have a random seed. The random seed is for reproducibility because you want to run two runs and you want the same numbers. Otherwise, you get a random number generator to be different seeds. You'll get different numbers, but distribution-wise, they should be the same. And we have some default prior that puts in on the beta and the sigma square. And then now we can change the prior. Things are indicated here using blue, the things we add on. Let's say I want the scale prior sigma square to be inverse gamma, shape 0.01, scale is 0.01, which is changed in here. So pi of sigma square is inverse gamma. And then I'm adding a random intercept model. Linear normal regression with random intercept is then I add a gamma j according to subject ID. And subject ID must be a class variable here. ID must be there. And the covariance prior is the R side, the G side prior for sigma gamma square. That's gamma j is normal 0 sigma gamma square, and the pi of gamma square is half Cauchy with degrees of freedom 2. And then if I have the random intercept model become a class variable D in here, and then my random, you can just change in the D to be here, and then this becomes a multi-dimensional random effects that have AR1 structure to have this side of the G covariance matrix in here. And then you can add a repeat measurements. That's just hypothetically to say that my model Y repeats over hours, and the repeater statement have type equal to UN and subject equal to person. Then you have a very easy simplification of in this case. So without looking at the BGLIMM procedural name per se, the remaining is very similar to mixed procedure and GLIMM mixed procedure in specifying the class, the model, the random, and the repeater statements fitting the model. Then once you switch to a different distribution, you can do Poisson, the different distribution. It's the same idea. You can change different link function. You can have offset. You can have no intercept and so on. You can add random statement with a subject equal to analyst in this example. And you can have a group option to model covariance heterogeneity, that the female might have a different covariance structure as a male. And then you can have nested or non-nested random effects. This is a, you have one level for analyst and one level run within analysts, random effects. So, and you can specify different prior distribution on a combination of different things that you can also use for BGLIMM. And next we will talk about a logistic regression. So the idea here is to build to show you from a simple logistic regression to logistic random effects model to repeated measurements with heterogeneity, and then extend to unbalanced repeated measurement models. The logistic regression example is fairly simple by nature. It's just two tests of treatment and the placebo are compared. Response variable is whether reported pain or not, and the covariates includes age and the gender of 6 patients and the duration of complaint and such and so on. So the treatment of A, B, and the P, and the gender is F and the M, and the female and the male, and there's a pain is yes or no. So that's that. And the logistic regression is considered to be a simple logic link between gender, treatment, and interaction between the two, plus age and duration. And they are dummy variables for all categorical predictors. And we're going to consider a normal prior with large variance as a non-uniformly prior on all regression coefficients. So the beta 0 to beta 7a parameters. So the following fits a logistic regression similar to what I had seen before, and I'm just going to explain them in a bit more detail. The data is input data set, random seed, number burning is 1,000 MBI, number of Markov chain is 20,000, and I'm going to think by 2. We don't have to think, but I just want to use it to indicate how to use the syntax. And then the output is equal to a data set samp out. It's the collection of posterior samples of all the model parameters, the random effects parameter, and so on. The model, let's look at the model statement. The model statement models the probability of pain, no pain, and pain. You can have the same trick as if you want to model the probability of pain equal to yes, then you specify the descending keyword after the response in the model statement. Okay. And then there's interaction between gender and the treatment. And you can see the treatment and the gender are all class variables, and then specify with a reference level. And the age and duration are the continuous variable. Distribution is binomial, and the coefficient prior, the beta prior normal, 0, and the variance equal to 1e to the 6th power. And the reference coding, it's one of the coding options in the PROC option in the class statement to create the design matrix for categorical variables. And the output are the following. You have model information to tell the response, binary, logit, fixed effects. Yes, there's no random effects just yet. And uses Gamma sampling algorithm with 1,000 burning, 20,000 simulation size, 2 thinning, a random seed, and number of threads. Number of threads just means that how many CPUs that you are using to do this. By default, it is 1, but you can certainly use or utilize all the CPUs that you have available to your computer. It produces the summary statistics on the intercept, the gender, treatment, and the interaction in the term, the age and duration. It has posterior mean, posterior standard deviation, and 95% HPD intervals for all of them. And then it also produces these things as trace auto correlation and the density plots. So we simplify it, called TAD, trace auto correlation and density plots of the trace, auto correlation, and density for every parameter. I just picked the interacting term between treatment A and the sex equal to female. And then you can see that there they have similar things in between. In a logistic regression, you can compute log of odds ratio. This log of odds ratio is just the logit of x of the ratio between x equal to y equal to 1 and y equal to 0 given x. It's the log of this is just the linear regression term. And suppose that you are interested in calculating the ratio of odds for a female population to the male population, then it's the difference is simply the beta 1 coefficient. If you work out the form, the difference between the two. And then the odds ratio is the exponential of the log of odds, and the exponential 1. You can just use the estimate statement to compute the female group and the male group between the two by accounting for the treatment effects. And there's some explanation here what these numbers 1 and negative 1s means and how different values are. For people who are familiar with estimate statements, then this is fairly standard stuff. But if you are not, you can maybe read the explanation and see how people use estimate statement to compute the linear combination of parameters. And then the slash of E gives the equation, the L matrix that's being displayed. And this is the estimate statement that the coefficient is on, or the sign is being, or the weights is being used on the coefficient, and to compute the odds ratio. You can also have posterior summary statistics for a GLM parameterization. The GLM parameterization is different from the summary statistics of this reference parameterization. I think this is just to indicate that I can run the same analysis with GLM parameterization versus a reference parameterization, and it supports in either way. But notice that there are things such as zeros. These are all included in the model because that's a GLM representation. Then the results of the log of odds ratio of a female and a male. The reason I say, sorry, this probably had to come out as appear to be nowhere. But what I was trying to say is that some people, depends on the parameterization, some people would see how to compute the log odds ratio more familiar one way versus the other. But by the end of the day, you can compute the log of odds ratio to be 1.65 between the female and the male group, and you can compute the odds ratio by exponentiate from the sample out data set of the female versus male attribute A variable, and this variable is what this variable generates. So this statement generates a linear combination of all the parameters, and it's named F versus M at treatment A. This variable is going to be saved as a sample out. So if you want not the log of odds, but the exponential of the log of the odds, then you take the sample out data set and you just compute the odds ratio to the exponential of that variable. Okay, and then you can afterwards use the sum-int macros to compute things such as the posterior mean, standard deviation, and HPDs of the odds ratio, or even plot the density plot. So here is how you would do logistic regression, and also infer on linear combination of functions or parameter using the results of the simulation. This is just a list of built-in Bayesian macros that computes various different types of statistics and diagnostics based on the outcome of a posterior data set. It also works similar, is a macro of the data set and the variable that sum in computes summary and interval statistics, but you can use effective sample size, MCSE, and so on to compute different Bayesian related quantities. Now we're going to extend this to a logistic random effects model. The logistic random effects model is just a random effects logistic with random intercept in here. In this example, we are investigating two medical procedures. We call it A and B. There are 15 centers. The center goes from 1 to 15, and there are two rows, two columns. Longer data set here. 15 of them are given A, and the 15 of them are given B in the same center. And you know the number of patients, and then the number of patients who reported side effects. Okay. So this is the data, and we're going to do a similar logistic regression, but in here we're going to have the side effects / n. This is events, n over events type, events over n's syntax. automatically puts this into a binary likelihood with logilink, and the group is the categorical variable, and a no-int option is used for you to better compare group A versus group B. Don't have to account for the intercept. And then there's a random intercept model with a group subject variable. Okay. Again, it's the same thing here as the model information table, the posterior summary statistics table. You have the group A versus group B. Random var is the measures variability of the center level intercept. This is the G-side variance parameter for the random statement. And at each center's intercept, they don't come out by default because there are 15 of them. In many attempts, it could be even more. So in the posterior summary and interval statistical table, it only displays the regression coefficients and G-side covariance, or and R-side if they're R-side variance terms. But since it's a binary model with no residual variance, we only output 2 regression parameter and a G-side variance term. The random effects parameter summary statistics don't come out by default, but you can request them by specifying a model monitor option in the random statement, same as the solution option in the mixed procedure and the mixed procedure. Yeah, it's same thing here. Is you can have to see the trace plot of group A, and then now you can look at the probability difference between group A and group B by computing the logistic transformation of the group B coefficients minus group A, and compute the probability. Look at the summary statistics of that distribution, and join the density of that. The shade in blue are the area that's of the probability difference is greater than 0, and the probability that the difference in probability greater than 0 is greater than 99%. It's a mouthful, but you can see that how easy it is to do Bayesian analysis to directly make a statement to say that the probability that there is a treatment and then the treatment difference is greater than 0, that probability is 99%. So it's part of the power of the Bayesian analysis. Next, I want to illustrate a case of repeated measurement model with heterogeneity. And the repeated measurement model just means a patient or subject has repeats over time. And again, this is a 2-treatment trial for patients with arthritis. Right? No, I'm sorry, I don't know how to pronounce that word. Rheumatoid, sorry, arthritis. So there are 67 subjects who enrolled, and then they will follow 3 time points, 1, 2, and 3. And in the data, you can see that the subjects, the first 3 rows coming from subject 26. At the time, they had the baseline measure of the strength of their hand grip. Okay? And then they retreat treatment 1, and then some receive treatment 2. The male subject, and the timeline is 1, 2, 3. And then the grip is 161 at time 1, 210 time 2, and 230 and 3. So these are the, over the treatment time, you want to see if the grip has increased over time as a result of the treatment. And then you can fit a 3-way interaction with variable gender, treat, and time, and also the baseline measure as a continuous variable. We can use within subject heterogeneity. So the unstructured type used in the residual side is the R-side covariance matrix. Okay. Just to see if there's a pattern and such. So the three-way interaction, gender, treatment, and the time is specified in the model statement. The baseline is a covariance, and we no-intercept the model. Now we add the repeated statement of time with the subject equal to subject. Subject is the first column. So 26 is one subject, 27 is one subject, 71 is for 72. And the type is UN is the covariance R-sided type. But the repeat variable time must be specified because time is used to indicate where the repeat is taking place. The option R and R core prints the estimated R matrix and estimated R correlation matrix. So the R is a bit confusing, but this is the standard. The R is not the variance because there are two variances, a G side and R side. This is R side covariance matrix and R side correlation matrix. And if you plot the data, you can see that of course there's a gender difference. Female tend to have weaker hand grip than male, but the strength change very greatly over time. Probably more with a variability in the male group than with a female group, and then you can argue saying that maybe one single residual side of the covariance matrix is not sufficient in capturing the two groups, and you put them into a group equal option to say group gender to say that they each have a different covariance structure. And now you can see that for female, you get one covariance matrix represented in blue. So here are the posterior density plots of the covariance matrices of COV11 for female, which is blue, and for male, which is green. Which is red. And so the female has variance around 300, and the male have 900. And you can see that the terms are different, and then the female have a diagonal variances more or less to be constant, around 300, but the male variance term increases over time, and you can see that the variability across indicates a great amount of variability as you go along as the time dimension. Of course, you can then add a more between subject heterogeneity by adding a random statement that has a random intercept by subject and a group by gender with a uniform covariance matrix and so on, which I won't go through in explaining the output of the detail. But BGLIMM is enable you to do these things at ease by exploring different complexity of a generalized linear mixed effects model by adding bits of things, and you don't have to take much of the computation burden in consideration. Okay. So the last example for PROC BGLIMM is unbalanced repeated measurement models, and I'll explain. Even though model syntax-wise specifying it's the same as a repeated model, the procedure does a lot of things underneath the cover. Here I'm explaining how the unbalanced thing works out. Okay, this is again a bits note on what repeated measurement model just means repeats as a time we had seen before. To set up to explaining how we underneath handling the unbalanced nature of the things need to a bit set up. And the setup is essentially to indicate that yi is a vector of dimension that covariance of R. R is considered to be n by n covariance matrix of the residual, and the P is the number of parameters in the size. And I have to say I have capital I subjects in the data. And R can certainly take different shape and different type. It's not an issue. Okay. So in a regression model with repeated measurements, says parameter vectors is beta and the residual. There's no G here. There's no random effects for consideration. It's easier to add them. It's not really an issue. We have the prior, we have the posterior, and then you subsequently sample beta giving R and R giving beta, and this is okay. This is just a multi-dimensional linear regression. Since you have beta and the residual and beta sampling, that's okay. And here just to show these all have known formula. One is a multivariate normal, one is inverse Bouchard, and the things are kosher. Now we are talking about unbalanced things. Unbalanced just means that some subjects have some missing values in the repeats. There are two situations as far as the data representation is concerned. One is on the left-hand side, you can see case 1, time is 1, 2, 3, 4, subject equal to 1, and I have covariance information, x, and then y has some measure, and then some measure are missing. Okay. So this is a situation where the x information are all known. You can think of x as covariance information that's known, but somehow, in some case, y just cannot be observed. Okay, and to the right-hand side, to the left, what I want to point out is left-hand side, everybody still has same number of repeats in every subject over time, 1, 2, 3, 4. However, it doesn't have to be always the case, is that to the second case to the right, person 1 had measurements of age at 8, 10, 12, and 14, and had a response measure, but subject person 2 missing a measure from age 14. So it have different number of repeats. So there are two different things. So the difficulty associated with modeling unbalanced repeated measurements is that the dimension changes. So for example, in first person, this y is 3, second person y is 2. In this case, y1 has 4 dimensions, y2 has only 3 dimensions. And conjugate typically is not available in regression. It gets to be complicated. And the alternative approach is to assume that we have ourselves a missing data problem. Okay, that's the power of the Bayesian, is that you don't see things in here where you don't see y. You can assume that y came from a missing value. Okay? But they are jointly normal distribution, 4-dimensional normal, but you just have a missing value in here that can obtain some information from within the group and between the group information. Okay. So we can treat the data that we have seen as the missing data and then become referred to as a missing at random mechanism. And the good thing about it is that it sets the residual R to be of the same dimension, and it makes computation easy. So if you denote yi is missing as the missing part of yi, observed is the observed part of yi, then all the missing values are treated as random variable. So they are sampled in the Gibbs sample. They are filled in first, giving the observed an x and the current sample of beta and r. And then once it fills in, this becomes a complete regression, complete data set up for linear regression, which we sample the beta and r subsequently. Okay. So in other words, I have a missing value here. They become missing value parameter, and these parameters then become part of the larger MCMC chain. And the sampling of the missing value of y is the result of a normal theory, multivariate normal theory, that's conditioned on the observed covariance matrix, and so on, with mean and the sigma square in a normal regression. If it's non-normal, then it can be sampled using Metropolis-Hasting. The remaining of the beta and R then carries through is in the balanced case for that reason. Okay. So this is the first situation. If we have only missing Y, but the covariance information is known, we can impute the missing response mu and sample missing Y as part of the Markov chain. But what if situations arise there's missing covariance? Okay. So here's the example. Case 1, I have 1, 2, 3, 4. The fourth observation, I'm missing both covariance and Y. Okay. Some cases that I can probably derive the missing covariance as a case to the right, where the first person gender is female and second person gender is male, and you can assume that this is just male, and then the linear regression can compute Y. But now, if I don't have this piece, the linear regression in here, mu of the missing value depends on the covariance information. If this is missing, then obviously I cannot impute this value. So the trick is to look at the residuals instead of the covariance by moving the regression piece from right to left. And so the residual itself is missing, but centered at 0 instead. And in here, with covariance missing, we just model, instead of model missing value of Y, we treat as covariance and epsilon as additional missing value and sampled, and they are centered at 0 with the right covariance matrix as a residual of the missing covariance. Okay, and then everything carries through. You can see that they in fact reach the same answer. And this is the plot that one shows fitted line of the regression line and fitted line on the residual line. You project everything here down to 0, and you get the same answer for it. Yeah, the actual value of the covariance become irrelevant because of the normal model that we have. You can extension to the mixed model is fairly trivial. You add the random intercept, or random effects parameters in the model to make it to be the same as the normally linear regression. Then it just adds additional sample of the random effects, the G side, and so on. And this is how internally PROC BGLIMM handles missing data or missing covariance data in the residual missing cases. We can go through this example, but its idea is the same here, where we have patient baseline drug and hour with data clearly are not balanced. Here are three drugs for different patients, and then some patients have the early and have missing, and some have later ones that are missing. Here just patient profile. We can have the unbalanced data. We can certainly expand it to the balanced data, but we don't need to in PROC BGLIMM. But expanding this is just to show that the data have missing values in here, and you can fill them in by the hour. The initial model that you can just fit a regression model with hour as repeats, subject is patient within drug, type is UN, and the nested effects is patient within drug indicates the repeats occurred for each drug treatment within a patient of 3 times 24 in total. Going back to see the data, that my first person is given a drug A times, but the same person is given drug B and different treatments as well. That's why there is a patient within drug option to have different groups. And then it estimated the R-side covariance matrix for this. Again, it's all done under the thing for the correlation matrix as well. And you can produce this in such a heat map of the correlation matrix, and you can even model different covariance structures if you want. So you can also indicate what I didn't show here is we can try different type of the covariance structures on the R side and identifies which one is a reasonable fit. But how you decide, and you can use a DIC as a way to handle it. And then adding the random effect itself is not that difficult. Again, you have a random intercept and the subject is patient within drug. It's the same thing by adding a random statement. Then it produces the estimates and so on. So that was the end of this example that we want to show. For the next few minutes, we will just go on and talk about more general sampling algorithm PROC MCMC. This last part is on PROC MCMC, and I'm pushing very close to the 2-hour limit, and this part will just be a very high level. I'm going through what's in it. The procedure by itself is a now more programming oriented procedure compared to PROC BGLIMM. PROC BGLIMM fixed a specific set of problems based on generalized linear mixed effects model that has a lot of built-in functionality through syntax specification. You don't have to do a lot. But MCMC is on the other side of the spectrum that you can fit many different models, but it requires, and then you can support a flexibility through supporting the data step programming language. You can define your own sampling function, you can define your own distribution, and you can do prediction and or so on. But it certainly requires a certain programming capability. This is very similar to NL mixed. What I am going to go through for the remaining 5 minutes is to highlight these slides, and hopefully the slides are self-explanatory, where you can go and look at them at your leisure and try out some of the examples in using MCM to fit different type of models. So the first part is to explaining what this is, and through a linear regression model to emphasize on the point that the specification of a MCMC program should mimic how you specify the model on paper. The linear regression is what it writes. You can change different components of the model, prior distribution, likelihood. You can introducing data step, change point to regression model, and so forth. And the next session explaining looping through the data sets, how PROC MCMC accumulates log posterior distribution for computing, and what prior statement means, and what model statement means, and the different type of models that it can fit, not only of the simple IID model, but also for data for different subsets of the data, autocorrelation, autoregressive type of data, and data that have dependency, complex dependency among observations. So what the procedure produces, that's similar to BGLIMM. And then the next section goes to the introduce the syntax, programming statement, what distribution that it does. So I'm scrolling through this very high level, including the sampling hierarchy, how it is multi-threading being done, the POM statement, their functionality, and of course how can you use a different option to choose different sampling algorithm, a study of convergence diagnostics in here. It also discussed, things as a nuts algorithm, what we had covered earlier, and what the prior statement does in specify prior distribution, how the model statement, how you can use the model statement for model multivariate data, and then how you can utilize programming statement and what to look out for in using the programming statement, and the type of distribution that it supports, and some notes on the gamma, inverse gamma, and inverse Wisher distribution, 3 of the very confused distribution in there, working with truncated distribution, working with censoring data, and working with array for multivariate distribution, and so on. I finished with 2 examples. One is working with non-standard distributions, a distribution that is neither normal, beta, or Poisson, or whatnot, and how to do that and what to look for, how you can use it for direct simulation to understand, for example, what the prior looks like. It's important if you have a prior, you don't know what it looks like, you can just use in MCMC to simulate directly from the prior, and you can simulate from complex joint distribution, a multi-dimensional situation. And then the last part is a random effects model, from the setup of it to introducing how the setup relates to the random statement in constructing a random effects in a model, and different type of random prior that you can have in the random statement of different options, and the importance of the subject variable, how to understand it, and making a link to some user who are comfortable with Wimbucks and how they link together, the conceptualize, and the complexity of using flexibility that multiple random statement that it offers with different usages, and a simple example of 3 ways of coding the same model with the joint modeling of two outcome of y1 and y2. You can do the long data format, you can use a short data format, and so on. And this is the end of the tutorial. I know the end is a bit rushed, but given that we have only 2 hours of the timeline, there is I'm hoping to provide as much information as I can. And as always, if anyone would like to get in touch with me, my email address is in here, and you can just send me an email if you have any questions that you have. So I wish you for the best, and thanks for listening to the tutorial. Bye-bye.